Okay, here we go with the video lecture for sedimentary rocks. So, to start it out briefly, what is a sedimentary rock? Well, it's really simple. It's a rock that's made up of the products of weathering. So, it's going to be made up of the materials that are created by the weathering processes. Generally speaking, sedimentary rocks only account for about 5% by volume of the Earth's outer 16 kilometers. Now, that 16 kilometers is actually a really important number. The reason is very simple. Below 16 kilometers, sedimentary rocks cannot exist. Generally speaking, sedimentary rocks contain most, if not all, of the evidence that we have for past environments. They provide information about sedimentary transport throughout the Earth's history, as well as containing fossils and economic resources, such as coal, natural gas, petroleum, magnesium, iron, gold, etc. So, how do we go from sediments to sedimentary rock? We have a lot of change that can happen from the time that sediments are deposited to the time that they become actual rock. Now, the general process is called diagenesis, and this is going to be all the physical, chemical, and biological changes that take place after the sediments are deposited. Generally speaking, this occurs within the upper few kilometers of the Earth's crust, and it's going to include a couple of different processes. It will include recrystallization, very much in the way that chemical decomposition will create more stable materials through the molecular changes of molecules, or the chemical changes in molecules. Recrystallization will develop more stable minerals from less stable minerals based on the fact that you're undergoing pressure and to a lesser degree heating. There's also going to be lithification. Lithification is where unconsolidated sediment are transformed into sedimentary rock. Now, this primarily has two components that happen in lithification. The first is compaction. So as you pile more and more sediment on top, the bottom layer gets under greater and greater pressure. That greater pressure is going to cause the materials to pack together more closely. So it's going to compact the material. Then you get cementation. Cementation is going to be where some mineral is left behind to cement the materials together. Generally speaking, there are three primary sediments, or three primary glues, if you will, that work in sedimentary rocks. They are calcite, silica, and iron oxide. Now, calcite you can tell the presence of by dropping a little bit of acid on the rock. If it fizzes just slightly, even if you have to listen to it to fizz, that shows that the calcite is present. Iron oxide is really easy to demonstrate because it's going to have a color left with it. It can be a dark black, gray, brown, red to yellow coloration. Now, generally speaking, when we look at the types of sedimentary rocks, we're going to categorize the broadest sense of type into those that are going to originate from mechanical or physical weathering versus those that are going to originate from chemical weathering. So we would call the ones that are from the chemical weathering would be considered crystalline. The ones from the mechanical weathering would be considered clastic or detrital, because we can use the word detritus as a term for the physical remnants of material that has been physically weathered. So we're going to look at the chemical rocks first and then come back to the mechanical based rocks, or the clastic rocks. So generally speaking, chemical sedimentary rocks are going to be rocks that are going to precipitate out from water. So in the chemical process, you have materials that are dissolved within water. Those are going to be the source materials for our sedimentary rocks that are chemically based. Generally speaking, this precipitation process is either going to be an inorganic process, i.e. through evaporation usually, or it's going to be through a biochemical or organic process. So let's go through the most common chemical sedimentary rocks or crystalline sedimentary rocks. The first of these, the one that's perhaps the largest group of the chemical rocks, is going to be limestone. Limestone is the most abundant chemical rock that there is. It's comprised primarily of calcite, CaCO3, and it has many different forms. In fact, the forms can tell you a lot about the environment in which the calcite was precipitated. Some of the forms include what we call sparry limestone or crystalline limestone. It's just crystallized calcite. We have travertine, which is a form of calcite that is laid down usually in freshwater or hot water deposits. We have oolitic limestone, which is a limestone that is really interesting because it looks like it's made of marbles. And if you cut each of the marble open, they look like jawbreakers because they kind of grew that way. So there's usually some sort of grain of some sort that started it. Could be the seashell of a foraminifera or a piece of seashell that was broken up. And it just kind of snowball effect or grew like a snowball rolling around in the limey mud until you have a whole bunch of these little marbles, for lack of a better term, that get themselves welded together and have the spaces in between filled in with calcite. We can also have fossiliferous limestone. Fossiliferous limestone is going to be, imagine a mass of fossils that is within a limestone matrix. The amount of fossils can vary from one extreme to the other, but as long as you have relative abundance of fossils present, you can call it fossiliferous limestone. We have coral reefs, which will tend to be categorized into fossiliferous sandstone. There's coquina. Coquina is really an interesting one. Imagine, if you will, a Rice Krispies treat that's made of seashells. That's literally what coquina looks like. Then there's also chalk. Chalk is going to be the microscopic shells of diatoms or plankton that have collected together. And that's the major categories of the calcites. Then we have Dolo Stone. Dolo Stone is very related to calcite. It is made of dolomite. If you remember, dolomite is calcite with a little magnesium added to it, so it has a slightly different set of properties to it. It's not as nowhere near as common as limestone, but it is a fairly common rock. Then we have the microcrystalline quartzes. These are basically different forms. Typically speaking, they're going to form from what we call a siliceous ooze in the ocean, probably usually silicic diatom skeletons that mass together and then solidify. Chert is usually what we also call microcrystalline quartz. The primary types of it that we would deal with are going to be things like chert, which is going to be kind of a dark gray color, flint, which is going to be kind of a lighter tannish color, jasper, which is a brownish red color. Then there's agates, which are the banded colors. So that can actually change what we call it, but it's still all could be classified as chert or microcrystalline quartz. Then we have all the evaporites, any sort of material that will dissolve readily in water and reprecipitate out that is naturally occurring. Salt halite is a great example of it. It's probably the number one example of it, followed by gypsum or rock gypsum, as it's sometimes called. But you can get other different salts that are found in the ocean in lower abundances. It's just a matter of you have to precipitate them out as the water body is drying up, so that you're getting a concentrated brine to get to the point where that particular mineral will crystallize out of the water. And then there's coal. Coal is a little bit different from the other rocks in that it's made up of exclusively organic material to begin with. It takes a lot of plant matter to make a foot of coal, on the order of about 80 feet of plant material to make 1 foot of coal at a minimum. Generally speaking, in order to form coal, you have to have a couple of very specific conditions. One, you need an environment that is going to be relatively warm, wet, and lush, so you have a lot of plant growth happening very quickly. But you also need that plant growth dying and piling up in a manner where it is in what we call an anaerobic environment, i.e. a no oxygen environment or a very low oxygen environment. You can get this in swamps. You can get this especially in swamps where occasionally it gets flooded and you get a silt or clay layer that comes in and covers up the dead plant material and seals it off from the atmosphere. But generally, you're going to have a couple of stages that you're going to go through with the formation of coal. You're going to have the plant material, then you're going to get what's the first stage, which is called peat, and then the second stage, which is going to be called soft brown coal or lignite, and then you're going to go to a slightly harder, darker coal called bituminous coal, and then finally, if you get enough pressure on it to cook it right, you get to the high carbon coal, which is called anthracite. Generally speaking, the darker the coal, the cleaner it will burn. Now, in terms of the detrital rocks, or the clastic rocks, everything is going to be based on particle size. That's pretty much it, with one exception for shape. Everything's based on the particle size. So, what are we talking about? Well, first and foremost, the mineral content actually won't matter. So it can consist of clay minerals, quartz, feldspars, micas, you name it. Any mineral can become a clastic rock. So what we're going to be looking at is by particle size. So how do we define particle sizes? Well, let's start with an easy one. Let's start with the idea of sand. Sand is basically a particle size distinction. It is a range of particle sizes, specifically between 2 millimeters in diameter, almost the size of the pencil lead in a regular wooden pencil, to as small as 1/16 of a millimeter in size. Now, why 1/16 of a millimeter? Well, it turns out that for the vast majority of people, the smallest particle your eye can individually separate out from another particle is about 1/16 of a millimeter. So that's about the visual limit of the human eye. So that makes a good cutoff for sand. Anything larger than 2 millimeters up to about 8 centimeters is going to be gravel. Anything larger than gravel is going to be, we can get into cobble, boulders, etc. as we go up in size. In fact, the full cutoff would read something like this. Yeah, we go granules, pebbles, cobbles, boulders for larger than 2 millimeters. Thankfully, for our purposes, though, we don't need to separate out those different sizes. Anything that is made of particles that are larger or contains a significant number of particles that are larger than 2 millimeters would be considered a conglomerate if the particles are round, or a breccia if the particles are angular. Okay? Again, between 2 millimeters and 1/16 of a millimeter is sandstone. Now, below this, we get into materials that are a little harder to distinguish without a microscope, but they're actually distinguishable. There is a way to do it. I'm not going to recommend it, but I will tell it to you. Okay? Between 1/16 of a millimeter and 1/256 of a millimeter is material that we consider to be silt. So anything that's in that size would be considered a silt stone, or sometimes referred to as shale in some circles. Now, below 1/256th of a millimeter, 1/256th of a millimeter is clay. Anything below that, anything made up of that is going to be shale or mudstone. Technically speaking, you could lump both of those, the siltstone, the shale, and the mudstone, and call it all shale. That is perfectly acceptable for our purposes. If you were to go into a higher degree of geology and looking at sedimentography and stratigraphy, you would want to make that distinction based on the particle size. Now, I'd said that you can tell the difference between the two. This is where geologists kind of chew on rocks. Yes, you heard me. I did say chew on rocks. It's not a technique I recommend you do, but there's a reason for it. Silt-sized particles will feel rough against your teeth. Clay-sized particles will feel smooth against your teeth. So if you've ever had a toothpaste that feels rough against your teeth, that's because it's the grit in it to help clean your teeth is silt-sized particles, whereas the ones that feel smooth, that's actually clay-sized particles. Okay? So, but that's pretty much it for the rocks. Conglomerate breccia, if it's larger than 2 millimeters and either rounded or angular particles, sandstone, siltstone, shale, or mudstone. Now, let me give you this warning about sandstone. Sandstone in and of itself, if you study deeper into geology, has a large number of different types based on what are the particles making it up, how well sorted are the particles, or what sort of shape are the particles. There's an awful lot of information in sandstone that we can read into it. So for examples, a sandstone that's made up of mostly particles of rock, usually angular to subangular, that are volcanic in origin, is usually going to be considered what we call a gray wacky. However, on the other end of the spectrum, a sandstone that's made up of nothing but well-rounded grains of quartz is going to be an Arkose sandstone. And there's a lot we can tell about the environment and what was the source of the material based on the type of sandstone and the nature of the materials within the sandstone. And we'll go over that in a little bit when we talk about some of the special beddings that we can see in them. Let's see. So just to go back over it, just to reconfirm it, we have two major classifications: detrital or clastic, and chemical rocks or crystalline rocks. The clastic ones are going to be discrete fragments and particles that are basically glued together. They all are going to have a clastic texture, whereas the non-clastic ones are going to have patterns of interlocking crystals. They can resemble igneous rocks, but they're usually much, much softer than igneous rocks. And that's the easiest ways to tell those apart. Now, one of the primary reasons that we like to study sedimentary rocks is we can actually determine information from sedimentary rocks about the geologic setting where the sediment was accumulating. And that which is going to help us know what the nature of the sediments that can actually accumulate are. Now, part of this is going to be based on energy. So let me cover this right now as simple as I can. Particle size in a system is dependent on energy. The more energy in the system, the larger the particle sizes that are deposited. The quieter the system, the more quiescent, the smaller the particles will be. Think of it this way. When you have water moving, the speed of the water is going to carry certain materials with it, usually up to a maximum size. It's carrying all the stuff as small as it can go, but all up to a maximum size. It won't carry anything larger than the amount of carrying capacity of the water, the competence of the water. So if you suddenly cause that flow of water to slow down, then it's going to start to drop out the larger particles that it's carrying. It's going to keep moving with the smaller particles. So we can really tell a lot about the energy of the environment by looking at the size of the particles. It also helps us if the particles are what we call well sorted by size. If the size of the particles are all relatively similar to each other, that's called well sorted, and that usually indicates a system that is undergoing some very specific, steady changes in energy to cause the sedimentation to occur there. Whereas if you have a sediment layer that is mixed of particle sizes, that's a more chaotic situation, probably something a little more something that starts out highly energetic and then drops a lot of energy, or reverses that direction depending on what the situation is. Again, it's something that you can learn to read in the rocks, but generally speaking, we can do that. We can also infer a lot by how rounded the material is. The more rounded the grains are, the further they've been transported. And that's simply because you have to knock those edges off the grains. When they are mechanically broken up immediately, they're very angular. If to become very well rounded, they have to travel a long distance and be abraded a lot. So we can really get into looking at the different aspects within the grains themselves. Even as much as orientation of the grains can tell you a lot about the nature of the system. In some cases, you can actually tell which way the water or wind was blowing. And we'll talk about that too in a little bit. So this brings us to the idea of the sedimentary environments. What is the environment that the sediments are being deposited in? Generally speaking, there are three primary environment classifications for sediments. Each one has multiple subclassifications. But let's just go over the three major ones first, and then we'll break them down further. So the first is going to be continental. In other words, these are going to be sediments that are deposited on the continents. Then you have marine, and these are going to be the sediments that are deposited in the ocean. Then we have what we call transitional. These are going to be sediments that typically are going to be in that transition between continental and marine. So what are some of the continental ones? Well, we can have all sorts of stuff. We have alluvial, which means it was deposited along streams or rivers. We have glacial, which means it was being deposited on glaciers. We have aeolian, which is a wind travel environment, such as you see in deserts. If you look in your lab book, page 54, there's a schematic that covers most, except for one, of the environments, and it starts on page 55 going through them. In the marine, you can have the shallow marine, which is depths up to 200 meters. You can have the deep marine, seaward to the continental shelves. You can also have things like a reef or a lagoon or barrier islands, tidal flats, which tidal flats can also be considered transitional depending on how much, how the water behaves in the tidal flat. And then the transitional one, tidal flats again are a good one. Lagoons are a good one. Deltas. And also I would throw in there swamps. I would consider swamps to be transitional. Now, we also can talk about the sedimentary facies. Different sediments often will accumulate next to each other at the same time. So let's imagine an ocean, if you will. Let's imagine an ocean with a beach. And let's say it's a sandy beach. So you've got sand on the beach. You got sand that goes out into the ocean. Well, as you go deeper and deeper out or further out into the ocean, at some point that sand is going to switch over to mud. So that's going to go from sand-sized particles to silt and clay-sized particles. Some distance out beyond that, you're going to get beyond where the particles are going, and you're going to start getting into limey muds, where you're going to have calcareous oozes or calcite materials depositing. So you would see a sequence of sandstone, shale, limestone. It's a very, very common sequence of sedimentary rocks for us to see, and it's a sedimentary facies that can actually tell us a lot about what's happening with sea level over time. So we can see the sequence where we see sandstone, shale, limestone coming in over each other. That's a sequence where sea level is rising and flooding onto the continent, and then we see it reverse with the limestone, shale, sandstone, sea level is going back out again. And we actually see that, and we'll talk about that if we get into geologic history. But these tend to occur over time and create these distinct units that we can actually follow. Now, we get into some really interesting things with sedimentary rocks in that they can be, you can have them being spatially sequenced or temporally sequenced. We'll get into that later on when we talk about geologic time. But I want to talk about some of the sedimentary structures because they provide very useful information about the Earth history. Now, some of the sedimentary structures include things like strata or beds. These are one of the most characteristic features of sedimentary rocks. These are basically the layer of sedimentary rock in and of itself. Now, in that and separating different beds, we can have what we call bedding planes. These are relatively flat surfaces that give us what was essentially horizontal at the time that sediment was being deposited. It can be a minor change in the way the sediments were being deposited, or it can be a minor stop of the sedimentation that can create a bedding plane. It can be, like in a large lake that might freeze over during the winter. You can get a different set of layers in there where you have finer grain material on top of slightly thicker grain material. And that finer grain material is going to have a bedding plane on top of it, and that actually represents when the lake froze over. We sometimes also refer to these as varves. We can have cross bedding. Cross bedding is a really fun one. I should draw that one out for you. Cross bedding occurs whenever we have sediment moving. Especially if it's moving in a single direction. So I'm going to draw it out here as if we're dealing with a large ripple mark or a dune. Okay, so this would be a large asymmetrical ripple mark or dune. The reason it's asymmetrical is you've got one side that's longer than the other side. Okay, one side. So this would be the lee side and the windward side. So this is the windward slope, this is the lee slope, or the slip slope, as it's sometimes called. So what's happening is the wind is blowing in this direction, and it's blowing sand up and over, and it's laying the sand down in a thin layer on this face at the front. Okay? Now, this is actually important. This angle here, we're going to call theta, is going to be the angle of repose. That is typically going to be close to, not always at, but it's going to be close to the angle of repose, which is going to be the steepest angle that material, based on its size and shape, can actually normally stack up at, based on all the different characteristics that it's under at the time. But what this does is if we do a cross section through this slope, what we see is we see all these faces lining up like that. Now, as this moves, it does not always scour back down to the original base. So what we might have is this level left here. So this is the cross bedding, where we have a layer, we have the two normal beds like this, but then we have these layers at an angle in between, almost like a herringbone pattern. In fact, if you reverse this, if this was to reverse direction and the next layer to have gone in the opposite direction, that's actually what you would see, is you would see something like a herringbone pattern. Okay. We see this in deserts environments. We see this in small ripple marks in a river system. So this is one of those features that we can actually look at. We can, if we measure the steepest angle on those faces, we can actually work out what direction the wind was blowing when those sand dunes were formed. And that can tell us a lot about the environment of the area. So that's cross bedding. There's also what's called braided bedding. Braided bedding is an interesting one in that it can be used to tell you a couple of different things. With braided bedding, what you have is a situation where you have a layer. Let's say the layer is like this. Bottom of the layer, you got a lot of big material. As you go up through the layer, the particles get smaller and smaller all the way up to the top. Okay? This can show you a couple of different things. If you're dealing with sediments that are derived in an oceanic environment, this is usually a marker for what we call a turbidity current. It would be in what we call a turbidite. That is the material left behind by an underwater landslide. If you're in a continental environment, this is a flood deposit. This is your typical flood deposit outside of the channel. You would see that the wave of the flood brings in a lot of heavier material. The lighter material, as the flood begins to recede, the lighter material is still being carried by the water, but the particles are starting to drop out based on their size as the energy dissipates. So this is the energy deposition. The energy depositional environment is becoming more quiescent as we go up through the section of the layer. So we can actually indicate information about the flood from that. So this is actually a very good indication of a flood deposit. In fact, actually, if you drive along I-19 from Nogales to Tucson, there are some spots in the road cut. Don't drive and look for them at the same time. I'm bad enough at that myself. But there are some places in the road cut where you can actually see layers like this that are clearly deposits from flood events that occurred millions of years ago. Then we also have ripple marks. Ripple marks are interesting because they can be asymmetrical, meaning that they are long in one direction, short in another, which usually indicates one single direction of flow, or they can be symmetrical, which means water is moving back and forth. Symmetrical ripple marks will tell you that you're in the presence of some sort of a large body of water, like a large pond or a large lake or even a sea or an ocean edge. Whereas asymmetric marks are going to tell you that you're dealing with maybe some sort of system where water is flowing in one direction, like a riverbed, or you may be working in a tidal flat where you have the marks are asymmetrical in one direction with different direction on top, showing the different tides moving in and out. We can also have mud cracks, which are where the mud dries out, it cracks apart, something that we see down here all the time, and then the mud cracks get filled in with a different material that will allow those cracks to be preserved. I actually have in my sandstone steps in the front, I actually have fossil raindrops. This is where the sand was wet or dry, it can be either or, and then had large raindrops hit it and leave little imprints in the ground, and then that got preserved. Then there's fossils, and there are many types of fossils. There are trace fossils, which are traces of life, so things like footprints, feeding marks, burrows, trackways, things of that nature. Then there are the actual body fossils. Typically speaking, in order to be a fossil, you have to be relatively rapidly buried in sediment. That's the real key. So the process of fossilization can take a various amount of time depending on the type of fossil that we're talking about and the conditions for it. But generally speaking, becoming a fossil, very rare event. And let's explain why. Just because I'm going to pull a name off the top of my head, and Charles, you happen to be it, you get to be the person we're sacrificing today. So if we take Charles out top of one of the hills here in the Rio Rico Nogales area, and he dies, and we leave him there, what's going to happen to the body most likely? Assuming people don't find it. The animals will, right? So the body will be scavenged. The buzzards will come, the bobcats might come, cougar might come, the coyotes and javelina definitely will come. The body will get scattered. The odds of the body being buried very, very low. Whereas if he happens to die in the Santa Cruz River during a flood event, there's a good chance his body could actually be buried in sediment right away, in which case there's a much better chance that the body will actually be preserved and therefore have a chance to actually become preserved through fossilization. We'll talk more about fossils later on, but that's generally what I wanted to cover with the idea of fossils. Fossils can be very, very cool. They can tell us a lot, and that's one of the dangerous things about fossils is that a lot of people might see a fossil and think that's cool and grab that one fossil, not knowing that there is a host of other information that is scientifically important about that fossil, about that animal, about the environment that the animal was in, that could be disturbed or even lost if the fossil is moved without being properly studied. So with that, I'll end it here, and I'll talk to you guys in class tonight.